This is lecture number 6. Hello everyone, welcome back. Today we are going to do some review of the thermodynamics. This is essential because as we discussed in the earlier class that most of the compressible fluid dynamics that we will be studying in this course will be related to the compressible flows, and for the compressible flow it is very important to have a good understanding about the thermodynamics, because you will have change in temperature and the internal energy, and there will be exchange of energy between the kinetic energy, internal energy, etc. So, we will review some of the thermodynamics aspect which will be useful for us for the CFD course. So, before we go to the thermodynamics, okay, I want to just recap the last class that we studied. So, we discussed in the last class that the gases are more compressible. So, gases are more compressible than liquids. Okay. And we also found out that if we talk about this isothermal compressibility, okay, tau T, which would be defined as minus 1 by V del V by del P at constant temperature, and the value of this was for an ideal gas which will come to 1 by P, and for at atmosphere temperature, let us say pressure equal to 1 atmosphere, which is 101325 Pascal. So, the tau T value will be around 10 to the power minus 5 meter square per Newton, right. And we said that for the liquid this tau T is of the order of 10 to the power minus 10, around something like 5 into 10 to the power minus 10. Okay. So, there is at least 4 order of difference, this is for water, okay, of this difference between the compressibility of water and the air. And then we derived the expression that our dV or d rho, if you say, it will become rho tau dP, right. So, because the tau of air is higher, for a given change in pressure you will have higher change in density, okay. And we said that if the change in density is more than 5%, that means your d rho by rho is greater than 5%, then it will be a case of compressible flow. We can no longer ignore the density here, density change here, right. So, finally, we ended with the thought that so this compressibility is a property of the fluid, right. So, now we have found out that the gases are more compressible than liquids, for at least 4 order more compressible than liquids, but is there any situation where we can treat the flow in a gas also as incompressible, right. That means the density change is less than 5%, right. So, I just want to give you one small example. Okay. So, there is a difference between flow and fluid that we discussed. The flow is something which is flowing. The flow, when the fluid has got motion, then it is a flow, right. So, if you have an aerofoil, okay, like this, okay, and let us say that you have some flow coming in, okay, and it is a low speed flow. Let us say I would say that this is around 25 meter per second, okay, and as it goes over the aerofoil it accelerates, and let us say it goes to a value of 50 meter per second, a max of 50 meter per second, right. So, this is my V1 and this is your V2, okay. So, what is the change in pressure, right. So, now there is a flow, there is a flow which is coming in. So, the medium is air, let us say the medium is air, okay, and the flow is coming in, and then because of that we want to find out what is the change in the pressure, so that it can give us estimate of whether the flow can be compressible or not, right. So, typically you cannot use Bernoulli's equation for the compressible flow, right. But here since the speed is very low, okay, so we can try to use the Bernoulli's equation and just try to estimate the change in pressure. Although it may not be that accurate, because even if the flow is subsonic or the Mach number is low, or basically flow is at low speed, then also you I mean the Bernoulli's equation ideally is not valid, it is valid only for purely incompressible flow, but the change will be not that high. So, let us say for this flow try to use the Bernoulli's equation, and you all know the Bernoulli's equation. So, if this is my point 1 and this is my point 2, right. So, this is P 1 plus half rho V 1 square is equal to P 2 plus half rho V 2 square. Okay. I am assuming that the flow is nearly incompressible, right. So, this P 1 minus P 2 will become half rho V 2 square minus V 1 square, and let us take for simplicity take rho is equal to 1. Okay. Its value is around 1.225 or something like 1.3 kg per meter cube, but for simplicity just take rho equal to 1, it will not change the conclusion that we want to find out. Okay. So, this will be 1 by 2 into 1 into 50 square minus 25 square. Okay. So, that is like 2500 minus 625. So, that will be around something around 1900 by 2. So, this is 950. Okay. So, around it will be this value will be around 930 or 950, right. So, then if you do P 1 minus P 2 by P 1. So, P 1 you can assume that it is an atmospheric pressure. So, which is basically our dP by P. So, this will be around 930 and P 1 is let us say it is 1 atmosphere. So, we can take it approximated to 10 per 5 Pascal, right. So, you can see the value is 0.0093, right. So, this is basically change is very small, the change in pressure is around 0.93%, okay, not even 1%. Okay. So, that is why we are saying that if the speed is very low, your change in pressure is very small, and despite the flow being compressible, which you can see here, still the change in density is not enough to consider this flow as compressible. Okay. We can make this relation more accurate, what Bernoulli's equation that we have, by considering the Euler equation, which we will discuss when we go to the conservation of momentum, right. But this is one aspect that I wanted to tell you, that when the speed is low, your change in the pressure with respect to the initial pressure is very small. Let us say now you change it to a higher value. Okay. So, let us say I want to say that it started with started with 400 meter per second and this went to 500 meter per second, right. So, in this particular case, remember this is a compressible case, typically you might be knowing about this speed of sound, and we will cover that again today, okay, more formally, but that is around 330 meter per second, okay, in the atmosphere for a temperature around 300 Kelvin and pressure 1 atmosphere, right. So, that is speed of sound. So, these both are basically more than speed of sound, right. So, these are the cases of your supersonic flow. Of course, I am considering the temperature and pressure conditions to the sea level, right. So, these are the cases where the velocities are more than speed of sound. So, these are cases of high Mach number, and you cannot use Bernoulli's there. You can use Euler equation there to find out what is the change in pressure due to the change in velocity, right. And you would find that this d rho is very high in that particular case, much higher than 5%, and you cannot ignore the change in density. If you are very simple minded and let us say applied the Bernoulli here for this case, which is not applicable, then also you will see that this P 1 minus P 2 by P 1 will be much higher than 5%, right. Because simply is that the change in pressure delta P varies as change V square, right. So, V 2 square minus V 1 square, right. So, when you do like this, you will find that the change is in the pressure is very high, and that is why the density change is very high. Okay, so I hope I convince you that as the speed increases, as the in other words the Reynolds number increases or the Mach number increases. Okay, so you would notice that the consideration of density becomes important. Okay. The another thing that is important, which is more useful, is what is the value of tau s. Discussed about two compressibility, one is the isothermal compressibility, another is isentropic compressibility, and by using P equal to rho R T, we basically found what is your isothermal compressibility, right. But in many situations pure flow is not isothermal, okay, but it can be isentropic, especially let us say take the same example that we had. Okay, we have an aerofoil, okay, and let us say this is your boundary layer. Okay, this is very close, this is your boundary layer, but if you go away from the boundary layer, okay, let us say in this region, okay, so flow is more likely to be isentropic. Okay. So, isentropic you might have read in the literature, it is a process which is both adiabatic and reversible, right. So, why the flow is going to be isentropic here? Because there is no heat exchange here, and secondly the effect of viscosity outside the boundary layer is not enough. Okay. So, there is the flow can be assumed to be reversible, right. So, in this particular case the flow is more likely to be isentropic. So, what is important is what is the value of tau s, okay, what is the isentropic compressibility. So, before we go into what is the value of isentropic compressibility and how do we calculate that, let us look at the entropy a little bit more formally, okay, and the isentropic processes. Let us review the laws of thermodynamics and then we will come back and calculate this value of tau s. Okay. So, first very brief review for a perfect gas. So, for most of the discussion we will assume it to be calorically perfect gas. Okay. So, that means your E will be equal to CVT and your H will be equal to CPT. Okay. If it is thermally perfect, we had discussed that will be D equal to CV dt. Okay. That means your Cp and Cv may vary with the temperature, but for normal practical conditions of nearly atmospheric pressure and temperature less than 1000 Kelvin, you can use this calorically perfect gas, right. So, for that those cases we can have this perfect gas equation. Okay. These are the relations of internal energy and enthalpy, okay, with change in with the specific volume at constant volume, specific heat at constant pressure. Okay. And Cp minus Cv, as you know, it is a gas constant R, okay, and we have discussed about the relation of R, okay, and the ratio of Cp by Cv is the ratio of specific heat, which is usually denoted by gamma, right. And if you use these two relation, so let us say Cp minus Cv equal to R. So, divide the both sides by Cv. So, this is Cp by Cv minus 1 will be R by Cv. So, this is gamma minus 1 equal to R by Cv, okay, and that is basically Cv equal to R by gamma minus 1. Okay. And similarly, because Cp is equal to Cv plus R, so that will be gamma R by gamma minus 1. Remember this these relations, because this will be using again and again when we go to the compressible CFD equations. Let us say for example, when we go to the energy conservation laws. Okay. Now, in the last class we discussed that the value of R, okay, it depends on the gas, because this is basically Ru by molecular mass. Okay. So, Ru is equal to 8.314, okay, joule per mole Kelvin, I think joule, or I think this should be okay. So, and molecular mass is so if you want to find out R of oxygen, or let us say R of air you want to find out, that is Ru by molecular mass of air, which is around 29, okay, and that will give you around 287, which is joule per kg Kelvin. So far so good. So if you are simulating with a different gas, you need to change the value of R, right, the gas constant in your CFD simulation. What about gamma? Okay. So let us say I am doing if I am using nitrogen or oxygen, okay, our value of R will change. Okay. But what will happen to our gamma? Will the gamma change in this case or not? Okay. So, as it so happens that the ratio of a specific heat, basically gamma, it depends on the degrees of freedom. So, what is the degrees of freedom? That what are the different kind of ways a gas molecule can change the energy. Okay. So, I without going into the discussion, so we can have basically internal energy for per degree of freedom will be around R T by 2. Okay. So, if you have n degrees of freedom, your internal energy will be stored energy will be d equal to n R T by 2, right. So, if you use the relation C V equal to, so C V equal to d by dt. So, that d by dt at constant volume. Okay. So, that will be become n R by 2, right, and if you use the C P equal to C V plus R, that will become n R plus 2 by 2, right. And then if you take the ratio of C P by C V, okay, you will get the expression which is equal to n plus 2 by n, right, where n is the degree of freedom. So, for the monoatomic gas, okay, you will have 3 degrees of freedom, okay, 3 ways it can exhibit the motion or it can basically exchange energy. So, in that case your gamma will be 3 plus 2 by 3, that will be 5 by 3, it will be 1.66. For the case of diatomic gas, which is hydrogen, nitrogen and oxygen or any diatomic gas, okay, so n will be 5 because you will have 2 extra degrees of freedom. Okay, because the diatomic molecule you will have 2 extra degrees of freedom. Okay, you can have vibrational energy. Okay, so then in that case you have n equal to 5 and gamma equal to 7 of 5 and that will become gamma equal to 1 by 4. So, this is the value that we use, let us say if you are doing a CFD simulation with air, right. So, here we assume that the content of carbon dioxide or nitrogen dioxide or NO is very small and it is largely basically 79% let us say N2 and 21% O2, it is largely diatomic. So, and the component of other gases is less than 1%. So, in that cases we can assume it to be diatomic and we can use this gamma equal to 1 by 4. However, if let us say if you are doing a simulation, if you change the medium and do the simulation let us say with ozone or carbon dioxide and so on and so forth, in that case you will have the degrees of freedom even higher, in that case n equal to 7, okay, and then gamma will become 7 plus 2 by 7 which is 9 by 7 and you have to use this gamma value of 1.33, right. So, coming back to this question N2O2, if you change from N2 to O2 you have to change the R, but the gamma will remain the same because your it is both are diatomic gases, right. However, if you go to like let us say your from this to let us say you go to helium, okay, in that case your both R will change as well as gamma will change, okay, you have to use the gamma of 1.66. Okay. So, these are some of the care that we need to keep when you are trying to basically set up your CFD simulation. Okay. So, first of all you have to understand whether you can assume it to be the calorically perfect gas. Okay. If it is fine, then what kind of gas is it? Okay, it is a diatomic, triatomic, monatomic and so on and so forth. Then you set up the gamma according to that, okay, and then you can set up the value of R based on the molecular mass of the gas, okay, and then you can assume the Cp and Cv to be constant if it is calorical perfect gas and set the value of Cp and Cv for that particular medium that you are using. Okay. Now, let us review the laws of thermodynamics very briefly, because I expect that you have gone through this course in your undergrad first year or second year, okay, and you have basic knowledge about this laws of thermodynamics. Okay. So, if you go to the first law, okay, so the first law is simply it is energy conservation. Okay. So, basically if you add heat anywhere which is this delta Q, so it is basically system and the surrounding. Okay. So, if the heat is added to a system, okay, it is used to basically increase the internal energy plus first law of thermodynamics, there are many different forms or many different ways of writing it. Okay. We will just sometimes they take this delta W to be negative, okay. That is when the system is work done on the system. Okay. So, if there is work done on the system, then the delta W is negative. If the work done is by the system, then delta W is positive. Okay. And for a reversible system, okay, if the system is reversible, that means there is no dissipation due to viscosity or other effects, then you can take this delta W as equal to P dV, and there are several derivations available in the thermodynamics course. Please go through that, and for that you can write delta Q equal to dE plus P dV. Okay. So, this is your first law of thermodynamics, okay, for a reversible system. Now, why we are talking about the reversible system, as we have discussed that if we are away from the places where there are viscous effects are important or dissipation is important, you will likely find the process to be reversible. Okay. So, that is why many of the theories that are developed in the literature is for the reversible, in fact reversible adiabatic flow, which is the isentropic flow, and the definition of entropy comes from the second law of thermodynamics, okay, where it says that the change in entropy, which is for any system, okay, which is given by your delta Q, basically if you are supplying some heat divided by the temperature, plus there are some losses due to irreversibility, okay, which is given by ds irreversible. Okay. So, it should be greater than equal to 0. That means that the ds reversible irreversible, okay, it will be basically greater than equal to 0. Okay. So, the overall, even if there is no heat transfer, okay, because of this dissipation, your entropy may increase, right. So, this is the statement of the second law, and it basically dictates which direction the heat will flow. Okay, it will flow in the direction where the entropy is always going to increase, because this ds irreversible is always either at the best case it will be equal to 0, if there is no dissipation there is no loss, otherwise it will be greater than 0, right. So, if we are talking about a adiabatic reversible system, if the system is adiabatic, then delta Q equal to 0. If the system is reversible, then ds irreversible equal to 0, okay, and then in that case your ds equal to 0. That means you can say that my entropy remains constant, S2 equal to S1 for any reversible adiabatic process from 1 to 2, okay, there will not be any change in entropy. Okay. So, that is what it says about the second law says about the isentropic system. It also gives you the definition of entropy, it gives you a handle which is called entropy and which is a state variable. Okay. So, you can calculate the entropy at 2, entropy at 1, and if you subtract the value of S2 minus S1, you can find out what is the change in entropy, and it has to be a positive number. Okay. S2 minus S1 has to be a positive, because either positive or 0, because that is a law that it always has to increase, the entropy has to increase. Okay. In this case I forgot to mention one thing. So, here the d is basically a state variable. So, you can calculate a variable at the end point and the first point, but delta Q and delta W they are not state variables, they are path variables, or it depends on the path. Okay. So, now we will basically combine delta Q and first law and second law and derive some very useful relations. Okay. So, we will combine both the first laws and second law, first and second laws, okay, and we assume the system to be reversible. Okay. Right now it is not adiabatic reversible, only reversible. Okay. So, in that case you can write delta W as P dV, okay, and delta Q can be written as TdS, because we are assuming that ds irreversible is equal to 0, because a reversible system. So, when you use that, so you have TdS plus is equal to Cv dt plus P dV. Okay. So, then it can be written as ds equal to Cv dt by T plus P by T dB. Now, we can use this ideal gas equation, which is P V equal to P V equal to R T, right. So, then it will give you P by T is equal to R by V, right. So, if you use these two relation, ds will become C V dt by T plus R d V by V, right. And if you integrate it, okay, let us say from point 1 to point 2 and assume it to be the calorically perfect gas, okay, 1 to 2, 1 to 2, 1 to 2. So, will get this will become S 2 minus S 1 will become C V ln T 2 by T 1 and plus R ln V 2 by V 1. Okay. So, one interesting thing you can see here, okay, is that even for a calorically perfect gas, the S depends on both T and V. Okay, it is a function of both T and V. Unlike our energy and enthalpy, which is only function of either pressure or volume, right. Here it is function of both T or B or T or P, whatever you want to say, right. So, it depends on T and it depends on V. Okay. And if we use the other relation, which is basically in terms of T and P, okay, and then you can write your H equal to, okay, let me mention here H equal to E plus P V, right, and this will become d H equal to d E plus P d V plus V d P, right. So, T d S can be written as d E plus P d V, okay, and that will be d H minus V d P, right, and that can be written as T d S is equal to C P dt, d H equal to C P dt minus V d P, okay, and this can be written as d S equal to C P dt by T and plus minus. So, now V by T you can use the same law P V equal to R T. So, that will become R by P minus R d P by P, okay, and if you integrate this you will get this relation, okay, H 2 minus S 1 equal to ln T 2 minus T 1 and R ln P 2 by P 1. So, your entropy depends on both temperature as well as pressure, even for the calorically perfect gas, okay. Unlike the other case where unlike the energy internal energy and enthalpy, which depends on only the pressure or the volume. Okay. So, with this we will stop for the class today. In the next class, we will discuss about the isentropic system. We will use this relation and see some interesting relations. Thank you.